Hey, hello and welcome back, everyone. I'm going to make it a quick one today because actually we're going to split this section into two. You'll see within the definition of the line integral, there's really two different kinds of line integrals, and so we'll be handling either of them separately. But the overall section is called line integrals and their fundamental theorem. So it turns out there's going to be a specific fundamental theorem of calculus, or as we just discovered, a specific generalized Stokes theorem. It's a specific version of the generalized Stokes theorem for line integrals. And in fact, these are going to be for the second day's worth of line integrals, the vector line integrals, not the scalar line integrals. But we will eventually see that generalized Stokes theorem apply to these objects, which we call line integrals. And what do we want to think conceptually about a line integral? Why would an integral be called a line integral? We're embedding a curve in higher dimensional space and integrating along that curve. So these really should be called curve integrals or path integrals. I think sometimes they are called path integrals. You can imagine if I have a curve here, and I'm going to orient my curve, just like we saw in the previous video. We do need orientations on domains, but for a line integral, the domain omega will be a curve or a path in a higher dimensional space. But because it's a curve and or a path, you can imagine thinking about a string embedded in the room in front of you right now. That string really is still a one-dimensional object, but it's embedded in a higher dimensional setting. And so these are going to reduce to one-dimensional integrals, the integrals we know and love from Calculus 1, even though they may initially seem like they're embedded in a higher dimensional space. That's what a line integral is going to kind of reduce to on its most fundamental setting. Let's talk about really how they get defined, and as I've kind of already mentioned, there's going to be two versions of this. So let's look at our definition here. So the first definition of a line integral, which is going to be, as you can see at the bottom, the scalar line integral. What are we going to do? We're going to give ourselves a curve C. So you'll see that C used half the time for curve, but almost interchangeably I'll use this gamma, so that's a Greek lowercase gamma, to refer to a curve as well. In reality, gamma is a function from a one-dimensional interval. And here we say, t min to t max. We're thinking almost about it like time, an interval of time. A function from a one-dimensional integral into Rn. The output of that function is Rn, and you can think about the curve simply as, this is very fancy math speak for the output of the function, right? The actual embedded output of gamma in Rn. Okay, so that, the curve really is, as I drew earlier, some shape, one-dimensional shape in higher dimensions, which has an orientation. Now you basically need gamma to describe that orientation, because without knowing which side is t minimum and which side is t maximum, it doesn't make sense to orient this at all. So in this case, we would call the left-hand side here t min, and then this kind of deeper right-hand side, we'd say t max. And in fact, that's gamma evaluated at t max and gamma evaluated at t min. So you can imagine as I'm putting different numbers into that interval, that's going to give me different points in n-dimensional space, or as I've drawn it here, three-dimensional space. And if you studied parametric curves in Calculus 2, then this is really the same thing. Gamma is just a parametric curve, or really a parametric function in any number of dimensions. So in Calculus 2, you probably studied parametric curves restricted to 2 dimensions, and you were talking about arc lengths and areas in those parametric curves. In 2 dimensions, now we can think about it outputting any number of dimensions. What would gamma often look like? Well, it's a function of t, but because the output of gamma is Rn, we often represent it as really a vector with n outputs inside of it. We should probably think about that as a point rather than a vector, but as we've been doing this whole semester, it's just a little prettier to think about the output of multidimensional functions as vectors. But really that's a point, the output is a point in Rn. So that's what these curves are going to look like. And we should define the scalar path integral. And a scalar path integral will actually, where's that word scalar coming from? Scalar is coming from the fact that there's another function here that if we look at the input to the other function is Rn, n-dimensional input, and just a one-dimensional output, also known as a scalar output. And so that's why we're going to call these scalar line integrals, because in essence what we're going to do, if I look at the definition of the integral at the bottom, so there's an integral over C, the domain of C, of this function, the scalar function f, and then ds, we just use ds to refer to the differential of the curve itself. So that's kind of a strange differential, but it of course has its own definition, which is the differential of the curve is actually the magnitude of the path, magnitude of the derivative of the path, and then times dt, right? That t is the variable of the path. So that's going to really be, this whole term here is really ds, the differential of the curve. And then, of course, we have the scalar field f, which we're evaluating along the curve itself, right? So f is evaluated on the curve. It's also integrated against the differential of the curve. And because our curve starts at t min and ends at t max, that's how we're going to compute the integral. But if we look at the bottom here, really what this last integral is, that is now reduced to a one-dimensional integral, just like we have from Calc 1 or 2. So in fact, we don't need to really learn much about higher dimensional integration to be able to compute line integrals, especially in this scalar sense, but we'll see that in the vectorial sense as well, that these integrals just reduce to kind of our one-dimensional integrals we know and love. So I will introduce the definition of the vectorial line integral here, but I will save the next video for actually computations, as well as introducing the fundamental theorem. But we'll talk about this vector line integral instead. And the only difference is that I'm kind of swapping out the earlier case. I had a scalar field that I would integrate over in a vectorial line integral, or you could just call it a vector line integral. I swap out the scalar field lowercase f for a vector field f vector. But the definition of the computation is going to be slightly modified. So now when we have, here's the same differential of the curve. Well, before it was just a regular multiplication, but now since f on the left-hand side, since that's a vector, we're taking a dot product of that vector against this differential of the curve, so we're going to form the differential also as a vector. So we'll take the differential of the curve also as a vector, and we're going to take their dot product. So here's now the differential of the curve, happens to be the derivative of the curve, since we assumed the curve was, vector valued. The derivative will also be vector valued, and then the output of f, of course, we assume is vector valued. So you're just going to take a dot product of the output of f as a vector with gamma prime, the derivative of the curve, and then integrate. So we just want to be clear, there are kind of two different line integrals depending on if the function we're integrating over happens to be scalar valued or a vector field. I have this remark at the bottom as well that we should discuss, which is that when I was first taking this class, I mixed up these definitions all the time between a scalar and a vectorial line integral. It's far too easy. I think I memorized the vectorial one right away because dot products make a lot of sense, and in fact this is the one that the fundamental theorem of calculus will play a role with. And so I memorized this one, and every single time I would try to complete a problem, I'd set up my line integral kind of fundamentally incorrectly. So, you could imagine if I accidentally threw a scalar in there, well, the dot product doesn't make any sense anymore, but I would always interpret that as a scalar multiple of gamma prime, and then I would get a vector as an output of this line integral. That's definitely not what we ever want. We always want both line integrals should, at the end of the day, just equal a single number. I'll mention that here. So even in the vectorial sense, you should get a single number output. In the scalar sense, you should still get a single number output. And so if you accidentally make one of your memorizations incorrect and produce the wrong line integral and you get a vector output, you did something wrong. So make sure you always get a single number as an output, and that should help you remember that in the case when f, the function you're integrating over, is a scalar valued function, make sure you put some magnitudes around the derivative of gamma. That's just my one little remark. I would make that mistake too often as a student, so hopefully you don't make that mistake. Discussing a little bit more about these scalar line integrals, that's what we're actually going to tackle today. Let's talk about what they actually represent. In the case where I'm just going to let this scalar be constantly 1, let's allow f to just equal 1 everywhere. So in the case that I let f equal 1, then the scalar integral gets defined as the following. It's defined as the integral from the minimum time to the maximum time of the magnitude of the derivative of my curve, dt. But I can think about taking this t on the inside of the magnitude just because it's one-dimensional, right? So as a one-dimensional vector, if I take the magnitude of dt, that's actually equal to the value of dt considered as an infinitesimal. Interpret it in the same way that like a one-dimensional vector space is equivalent to a space of scalars. And so you can pull that dt through the magnitude, and then if you do, right, this is a little bit poor notation, but you can imagine we're canceling those dt's, and what's really happening here is we're computing the magnitude of the total derivative of gamma. And when we think about it that way, the magnitude of the total derivative of gamma, the magnitude is just referring to the total length of the total derivative, which is the total change, right? So this is referring to the total length of infinitesimal change, of gamma, and then added all the way along its path, added all along its path. Well, as an image, what does that look like? Here I've taken some curve, so imagine this is my curve here. So I've taken this curve and I've split the curve into, well, not technically infinitely many, but a very, very large number of vectors. In other words, these are the differentials of gamma. You can think about each of these arrows as the differential of gamma. So I'll say that arrow equals differential of gamma. But then if I put the magnitude around that differential, I'm putting the magnitude around the arrow, I'm simply asking what is the length of each vector. And if I add all the lengths together, especially as I get smaller and smaller vectors, if I add them all together, what am I actually going to arrive at? Well, each vector itself is kind of a one-dimensional object, but I'm adding all those together to recover kind of the total arc length of that curve. And so that's what we think about in the scalar setting when we let this function be constantly 1. In other words, if I want the arc length of a curve and I have a path which describes the curve, just take the integral from t min to t max. I've got the mins and maxes backwards here, min, max, of the magnitude of the differential of gamma, and you'll recover the arc length. And so that's just a really nice way of getting arc length of any curve in any number of dimensions. But let's think about the case when maybe my scalar field isn't constantly 1. If my scalar field isn't constantly 1, then what we're thinking about is we have this curve that's embedded in space. So maybe there's my curve embedded in space, and the curve is passing through a cloud. If I write this version, curve C, F, ds, then C, this curve, passes through a cloud of local density F. You can imagine if I were an airplane, one of those trick airplanes that can fly in many, many directions, and I'm literally passing through a cloud. Big question would be something like, how much water vapor, or cloudiness, do I accumulate along the path? So there's going to be some locations where the cloud is particularly dense and other locations where there's almost no cloud. And the line integral is basically asking the question, if I add every little bit of cloudiness at every point along the way, how much total cloud do I pick up? Like if I'm actually flying through it, how much water vapor, moisture ends up on the plane? When I'm flying through more dense areas, I'm going to get more moisture. Less dense areas, I'm going to get less moisture. And then the integral is just going to add kind of the total accumulation of that moisture along a given path. But there's nothing really special about this idea of a cloud. It could represent any measurement. So it's kind of just the local density of anything you want to measure. And so I kind of mentioned below here that you could think about this as if you have F representing the proportion of gold embedded in some granite, like in a mountain. That's really the density of gold. So this F represents the density of gold. And then the curve kind of represents a mine shaft that's been drilled through the mountain, some curve through the mountain. If we integrate that proportion of gold along the mine shaft, you're really just asking what is the total amount of gold that's been extracted, right? Not the total amount of rock. That would be kind of if F were constantly equal to 1. I mean, you kind of just get the arc length then, but total amount of gold, because F is now representing kind of locally the proportion of gold at each step along the way. So that's what we think about with these scalar line integrals, kind of just the total accumulation of some object along F. And now there is one extra interpretation, because you can think about total accumulation. Imagine if F is now describing the height of really a cliff. I say a cliff face, but you could think height of a mountain. So the height of a cliff face or the height of a mountain, and the curve C describes the curve as seen from above, which describes kind of the edge of a cliff. Then this line integral, same line integral as before, it's just going to now talk about the total surface area of the cliff face, because what you're thinking about is, okay, so actually this base is the curve that's traveled, right? So the base is the curve C, which is traveled, but then you have the function which describes the height of a cliff face the whole way. You can think about like total accumulation of area. You're right, because the function is kind of describing the density, or whatever you want to think about corresponds to the height of the cliff. You're adding up all of these heights along the path C, and you're going to get kind of the total facade, or cliff face area. So this integral F ds along C gives area of cliff face. That's kind of specific to the event when F has 2 input dimensions and then a single output dimension, Z, we'll say. That's really a specific setting there, but you can think about it as the area of the cliff face. So all of these are kind of similar applications for the scalar line integral. Arc lengths, kind of total accumulation of some quantity over a density field, and then in this final setting, the area of a cliff face, whose curve, as seen from above, looks like the curve C. So now we're going to calculate some of these, and to calculate a lot of these, I want to mention in this remark that the Pythagorean identity is going to become invaluable. So this is that identity. You'll probably recognize it right away when you see it, but I want to prepare you all to see it again before we start using it all over the place. This identity looks like sine squared plus cosine squared. The variable doesn't matter as long as the variable is the same. In both sine and cosine, sine squared plus cosine squared is equal to 1. A quick rearrangement, so you can imagine if I divide both sides by cosine squared of theta, well, cosine squared is canceling, and we'll get a 1 there. Sine squared over cosine squared is tangent squared, and 1 over cosine squared is secant squared. So kind of another version of this Pythagorean identity will be tan squared plus 1 is secant squared. And really either of these will show up all the time. Why will these often show up in scalar line integrals? It all comes down to when you take the magnitude of this path, well, I guess the derivative of the path. Well, magnitudes are the square root of each entry in the path. I think it's derivative squared. So it's that square root all added together, and a lot of professors and a lot of example problems are going to set these up to have at least quite a few of these derivatives be sines and cosines, so that hopefully you can find a sine squared plus a cosine squared equal to 1. And even in the event that you don't find them equal to 1, you may end up having to, if we're integrating against this, right, integrate against it dt, integrate against it dt, how do you integrate the square root of quadratic terms using integration techniques? That's going to be trig sub. So trig sub integration techniques might start to show up in this section as well. This is really the main reason you learned it in Calculus 2, is because it lets you handle arc length problems, and really arc length problems in any number of dimensions. So please keep that in mind, either the Pythagorean identity or its neighbor or trig sub, all as valid ways of solving our problems. And with that said, let's get into maybe the first example problem. We're going to try to compute the arc length of a helix described by the following paths. This is gamma, which goes from 0 to 6 pi, outputting an R3 divided by t minus 3 pi in the first entry, 4 cosine t in the second, and 4 sine t in the third. Why is this a helix? Well, you'll notice in the YZ directions, we have kind of this notion of a circle. Because I don't know if, once again, if you remember your parametric curves from Calculus 2, if the x component is equal to cosine and the y component is equal to sine, well, it should feel like a unit circle. It feels like a unit circle, but in this case, we've multiplied everything by a 4. So it makes a circle of radius 4, centered at, in this case, in the y and z direction, centered at 0, 0 in the y and z direction. So what would that look like here? I guess it probably looks like the circle given here. It would look like that if it were just a circle, but what's happening in the x direction is that we start at negative 3 pi, and then we move forward in the x direction as t evolves. And so really you start out here, but as x evolves, you start rotating around that x-axis. And I don't know if I drew it perfectly, but these terms are rotating us around the x-axis, while t in the x direction is just pushing us forward within that x direction. So that's why we end up with a helix here. These are kind of a common curve to try to find line integrals over, because Pythagorean identity will show up with these curves, so people like to include them as example problems. And let's go ahead and actually compute the line integral, which would in turn compute the arc length. So we're going to take the magnitude of the derivative of this path, and then we're going to integrate from, I guess, 0 to 6 pi in this case. Well, to get the magnitude of the derivative, we will definitely need the derivative, and to get the derivative, we just take d dt, and we're going to apply it to each entry in the vector, and it looks like for some strange reason I decided to change my problem from 3 minus t pi to 3t minus 9 pi. So let's assume that 3t minus 9 pi was correct, and so we're going to take a derivative of 3t minus 9 pi to get 3 in the first entry, derivative of 4 cosine t to get negative 4 sine t in the second entry, and then derivative of 4 sine t to get 4 cosine t in the third entry. And I can see now why I wanted this multiple of 3 on top of t, because when I include a multiple of 3, eventually we'll end up with a really nice square root. But let's actually go through that computation. We've taken a derivative of gamma. If I'm going to use the arc length formula, I need the magnitude of the derivative. So to get the magnitude, I'm going to square each entry. So 3 squared, negative 4 sine t squared, and 4 cosine t squared. And I'm going to add those all together and compute one giant square root. Well, 3 squared happens to give me 9. And the negative 4 squared on sine will just give me a 16 sine squared, and 4 on cosine will give me another copy of 16 cosine squared. And here you can see that Pythagorean identity show up. So we want to make sure we use the Pythagorean identity and say this is actually just 9 plus 16, or root 25, or 5. So it turns out that the magnitude of the derivative of this function is just 5. Meaning, if I want the arc length over this curve, I just take the scalar line integral against 1, and I integrate from 0 to 6 pi, magnitude of the derivative, which we just calculated was 5. The antiderivative of 5 dt will just be 5t, evaluated on 0, evaluated on 6 pi. We'll get 5 times 6 pi minus 5 times 0. We get 30 pi. So it turns out the arc length of this helix is 30 pi. Now we'll compute two scalar line integrals with non-constant scalar fields, right? So these are now referring to kind of this total accumulation idea. So suppose this represents the density of a cloud. Cloud of something that we're measuring, and then gamma represents a path in three-dimensional space. What would the total accumulation of the density here, whatever this cloud happens to be, what would the total accumulation be as I complete gamma? Now, if I happen to plot gamma here, not that it's important, but maybe useful to get used to seeing some of these things. I've got a cosine and a sine in the x and y variables, so that's a circle in the xy direction. And z is constantly 1, constant z direction. That just gives me a circle in the xy direction at a height of 1 on the z-axis. So that's what gamma is going to give me, it's just that circle. So I guess we're asking, was the total accumulation of this density field, whatever we want to think about it as, along the circle that sits at a height of 1, horizontal circle at a height of 1. Well, to do that, let's just set up the integral. We've got the integral f over this curve ds is going to be integral t min to t max of f of gamma of t, now multiplied by the magnitude of the derivative of gamma dt. So once again, we'll need that magnitude of the derivative. Let's go ahead and compute a derivative of gamma. To do that, I'll do a derivative of cosine, which is negative sine. I'll do a derivative of sine, which is cosine. I'll do a derivative of 1, which is 0. And the magnitude gets particularly easy here, right? Because if I take negative sine, square it, I get sine squared. If I take cosine, square it, I get cosine squared. If I take 0 and square it, I don't get anything. So my Pythagorean identity just gives me the square root of 1, which is 1. So this term happens to just be 1, and life gets very easy. All I have to do is actually evaluate f along gamma. So let's recall f of x comma y comma z was x y squared z cubed. If I'm evaluating that along gamma, when we remember gamma was cosine, sine, and 1, we're just going to plug a cosine in for x, we're going to plug a sine in for y, and we're going to plug a 1 in for z. That's why we see here a cosine in for x, a sine in for y, so it's sine squared, and a 1 in for z, as well as a multiplicative 1, which was coming from the magnitude of the derivative of my curve. Simplifying everything, what do I see? I just see sine squared times cosine. This happens to be a u sub integral with u equal to sine t, so that du is cosine t dt, and we end up with u squared. Now I did have to modify my bounds. What happens when I plug in 0 into the value for t? I get sine of 0, which is 0. What happens when I plug 2 pi in for t? Sine of 2 pi is also 0. And so my new bounds are from 0 to 0, which, surprise, surprise, what's the integral then when my bounds are the same? Especially in this case, my integral is just going to be 0. So it turns out my total accumulation, now we shouldn't really call it accumulation necessarily because there's some version of like depreciation or whatever the opposite of accumulation would be when f is negative. We allow ourselves to lose some of whatever we're trying to collect is 0. So in this case, because it's that closed circle, it looks like probably I was accumulating a little bit of something in my cloud, but also losing something in my cloud, so that when I make one full revolution, I just end up actually at a value of 0 here. Now this very last one, we want to caution the reader, it's going to be quite intense. We're using all sorts of integration techniques that you remember, hopefully remember from Calculus 2. And if you don't, I don't want to say it's the end of the world. Most professors won't ask for something quite as hard as you're going to see here, but they maybe will be testing on trig sub at least once, or maybe some other integration techniques at least once, just to see that you're still nimble. But this problem is going to be very hard. So let's get ready for a lot of integration techniques, but don't be too terrified if it seems too much work, because this is not really a problem a professor would often ask you to complete. So what is this problem? We've got a scalar line integral, and I've got a little typo up here. It should be from R2 to R. So I've got this scalar function, f of xy is x squared plus y, that describes my density field. And suppose I want to integrate it along the curve 1 minus 2t, 1 plus t squared, where t goes from 0 to 1. Seems pretty innocuous, right? We had an integral, it was what, x squared plus y ds along this curve. And so when I write this down here, from 0 to 1, there's my t minimum to my t maximum. We're going to evaluate x on gamma's x output, so that'll be what, like 1 minus 2t squared, and we're going to evaluate y on y's output of gamma, so plus 1 plus t squared, and that term will multiply by the magnitude of the derivative of gamma, and the derivative is pretty easy to compute here. The derivative of negative 2t is negative 2, and of t squared is 2t, so if I compute the magnitude of that, I'm just going to square negative 2 to get 4, I'm going to square 2t to get 4t squared, and we end up with 2 root 1 plus t squared, so something like 2 root 1 plus t squared here, and dt. Okay, so the integral maybe doesn't look amazing, but it kind of just looks like polynomials and maybe a single square root sitting there. So why should that be too bad? Especially if we go ahead and simplify it, we can kind of expand the x squared plus y term and simplify. We get 2 minus 2t plus 2t squared times the magnitude 1 plus t squared dt. Or in other words, if I kind of pull a 2 out of every term and in fact split my integral at each of these pluses and minus signs, we're going to end up with really 3 integrals. The first one, integral of root 1 plus t squared. The second one, integral of t times root 1 plus t squared. And the third one, integral of t squared times root 1 plus t squared. Still doesn't look particularly scary, and yet if we go through the work, even on this first integral, we've got the integral of 1 plus t squared. How do we integrate square roots of quadratics? We must use trig sub on square roots of quadratics. And if you don't remember which trig sub you're supposed to use, because it's a 1 plus, that's the important part here, 1 plus, and maybe you remembered from earlier, you saw tan squared theta plus 1 equals secant squared theta, because we've got this plus 1 here and the 1 plus in our square root. Yeah, we want to use tangent as our trig sub trigonometric function. When that happens, you take dt, you get secant squared theta d theta. And also, you're allowed to kind of, when you make that substitution, you get 1 plus tangent squared in the square root. And because of that Pythagorean identity, 1 plus tangent squared is just secant squared. So this simplifies to the square root of secant squared is the secant cube because of the extra secant squared coming from the derivative of t. So now we're integrating secant cube. And this is where things start to feel like maybe they're a lot worse. I also want to mention, some people are going to wonder, why did the 1 switch to a pi over 4? That's just because if I'm plugging in a 0 for t here, that means that, well, theta will still stay at 0 to preserve that tangent of 0 equals 0. But if I plug a 1 in for t, that's this upper bound, then what would theta have to be to preserve that tangent of theta is equal to 1? Well, theta would have to be pi over 4. So that's why the upper bound became pi over 4. Anyway, we've basically reduced our problem to now calculating the integral of secant cube, and that one does not seem easy. This is where kind of all hell starts breaking loose, unfortunately. Let's go through the integral. Secant cube, how should we integrate that? We're going to do it using integration by parts. So another throwback of integration techniques here. If I have the integral of f times g dx, this is going to be equal to the antiderivative of f times g minus the integral of the antiderivative of f times g prime dx. Or maybe you saw it as v du in some cases. But either way, we happen to be integrating one of the two functions on the inside of an integral, and we happen to be differentiating the other of the two functions inside an integral. Now it turns out it's not too bad to do that here, because in fact we know how to integrate secant squared, we know how to differentiate secant, and so hopefully we're off to the races. So to differentiate secant, the derivative of secant happens to be secant tangent, and then the integral of secant squared, if you recall d d theta of tan theta is a secant squared, then the integral of secant squared just happens to be tangent. And so we've got g here, g, we have capital F, the integral of secant squared here, and then we have kind of the derivative is taking care of one of those tangents. Secant tangent is the derivative of secant, as well as a second copy of tangent coming from the antiderivative of secant squared. So that's how we're going to start this integration by parts. And then the next step is actually to recognize that by the Pythagorean identity again, if we just take tangent squared theta plus 1 equals secant squared theta, and we subtract 1 from both sides, we see that tangent squared is actually secant squared minus 1. And if we go ahead and simplify this integral as 1 copy of secant cube, as well as negative, so a positive 1 copy of secant, then what we get out of our integration by parts is, well, we started with the integral of secant cube, and we've recovered an integral of secant cubed. So this is one of those fancy integration by parts where we pull this integral left and divide by 2. So we're going to pull that integral to the left and divide by 2. Turns out we know how to integrate secant, and we've already integrated this term here, so we'll end up with something that we can actually compute. Now the integral of secant, this is usually something you just look up in a table of integrals, happens to be logarithm secant plus tangent, so we know how to integrate that. And so this integral of secant cube happened to be, because I've got a 4 out front, but I also divided by 2 when I brought things over. It ends up being 2 secant theta tan theta evaluated on the bounds, as well as this antiderivative of secant, which is 2 copies of log secant theta plus tan theta, also evaluated on the bounds. Now when we plug the bounds in, we plug in a pi over 4, which for those of you who remember, secant pi over 4 is root 2, tangent pi over 4 is 1, secant of 0 is 1, tangent of 0 is 0. We're going to get the same down here. Secant pi over 4 is root 2, tangent pi over 4 is 1, secant 0 is 1, and tangent 0 is 0. So if we simplify a little, 2 root 2 plus 2 log 1 plus root 2. So that was all the work done just to integrate this single term of the 3. So I've still got this term and this term to take care of to find my scalar line integral. If we want to tackle that middle term is a little easier. Middle term, if you remember, was t times the square root of 1 plus t squared. And in fact, recognizing there's a t out front and then sort of a function in parentheses, this does set itself up nicely for a u sub, where we let u be that internal function 1 plus t squared, meaning du would be 2t dt. You can extract one of the 2's from the 4. And we find our 2t dt over here for du, meaning that our life gets somewhat easy. We're just integrating square root of u, or integrating u to the 1/2 du, so the power rule says that that's u to the 3/2 over 3/2. Then we evaluate our bounds at 2 and 1, because that was, once again, if I plug a 0 in for t, that means u on the bottom will be a 1. That's why I have a 1 here. And then if I plug instead a 1 in for t, that means u on the top will be a 2. So I get a 2 on the top. So I'm going to plug in a 2, plug in a 1. We end up with 4 minus 8 root 2 over 3. So that's the second of the 3 integrals that I have here. I've computed that one as secant cube. I've computed that one using some u sub, and now I've got this one, which perhaps is the worst of all, because it's actually going to be a combination of both. Now that we have a t squared out front, you can imagine that's really t times t root 1 plus t squared dt, where I can use integration by parts to find an integral of this term, because that was actually the term I just tackled, and I can quite easily find a derivative of this term, because the derivative of that term will just be 1, but I'll actually have to go through that integration by parts work. So when I go through the integration by parts work on that term, right, what have I done is I've separated that t squared into a t and a t. And in fact, I've brought my 4 all the way through just because we've already computed that integral. When I do integration by parts and I take the integral of this term, that happens to be the u sub integral I just computed, so I know it's equal to this, u to the 3/2 over 3/2, and that's why I have this u to the 3/2, and I've already simplified a 3/2 there. This is from integration by parts, that's capital F times lowercase g minus the integral of, well, g prime, recall, is just equal to 1. If g is t, then g prime is equal to 1, so g prime is just 1 times capital F. Here's capital F again. So now I'm integrating this version of capital F, and once again I have a square root of a quadratic, and so I need trig sub. In fact, the same trig sub with tangent. Now I went ahead and actually evaluated on the bounds on this first term. You get an 8 root 2 over 3 for the first term. That's not going to play a huge role, but it's kind of nice because it actually cancels with the 8 root 2 over 3 that you get from the earlier case when we simplify everything at the end. What's more important is this final integral of 1 plus t squared to the 3/2 power that we're going to have to run one more round of trig sub on. So when I run trig sub on that, we're still going to have 1 plus tan squared as the trig sub term, and we'll still get secant squared theta d theta as our dt term. And when we use the Pythagorean identity on the 1 plus tangent squared, we're getting secant squared to the 3/2, and of course the squares can cancel. We'll just have a secant cube there. Secant cubes times secant squared, and we're integrating secant to the 5th. Once again, these bounds were modified from 0 to 1. If I plug in a 0 for t, then theta also needs to be 0. But if I plug in a 1 for t, then theta needs to be pi over 4. So that's why I get pi over 4 in my upper bound. Okay, secant to the 5th. How are we going to tackle that? We're going to tackle it the same way we did before, because we still recognize that secant squared is once again easy to integrate, and secant cube is easy enough to differentiate. It's not easy to differentiate secant cube, but it's just a chain rule, right? You're going to get a 3 that comes out front, and then secant squared times the derivative of secant, which will be a secant tangent. So that's what we see here, right? 3 secant squared times secant tangent. That's the derivative of that secant cube term. But of course, the antiderivative of secant squared is, again, just tangent. And so here is one more integration by parts. We have capital F times G here, and we've got G prime times capital F over here. What does everything simplify to? Well, we know how to evaluate that. That's just going to be plugging in the bounds. Over here, things simplify. If I pull my 3 out front, I just get a 4 out front. And then what else simplifies? I have 1, 2, 3 copies of secant, and I have 1, 2 copies of tangent. We're going to do the same thing we did before and run the Pythagorean identity in reverse and say that tangent is actually secant squared minus 1, so that now I have 5 copies of secant if I distribute this secant minus a single copy of secant cube. So there's a minus a single copy of secant cube. In this case of secant to the 5th power, once again, because that's the integral we're trying to find, we just pull it to the left-hand side. And in this case, because we want to preserve a negative 4/3 out front, negative 4/3 minus 4 is negative 4/3 minus 12/3 is negative 16/3. If we want to take negative 16/3 and recover a negative 4/3, we have to divide both sides by 4. That's why we're dividing both sides by 4, because 16/3 divided by 4 is 4/3. Well, what is that going to leave us with? That'll take care of this term, because this term will now be brought over to the left. And after dividing by 4, this will be a 1/3, and this will be a 1. It'll leave us with a single copy of a secant cube antiderivative, which thankfully we've already computed. That was this one all the way up here, right? We've got the antiderivative of secant cube up here, and thankfully the bounds are the same. So we're going to use that antiderivative or integral of secant cube, same method that we had before, to recover what it's equal to. So that's the same method we used before. And finally, we can plug in our upper and lower bounds on all of the remaining terms. Recall, secant of pi over 4 will be root 2, tangent of pi over 4 is 1, secant of 0 is 1, and tangent of 0 is 0. Secant pi over 4 is root 2, tangent pi over 4 is 1, secant pi over 4 is root 2, tangent pi over 4 is 1, secant 0 is 1, tangent 0 is 0, secant 0 is 1, tangent 0 is 0. Time to simplify. What do we get? We get negative 7 root 2 minus 1/2 log 1 plus root 2. Now that answer was just this integral, or equivalently this integral, and this integral was just half of the third integral we had at the top. We still have this 8 root 2 over 3. So now we have fully finished each of our 3 integrals. We had this one first as secant cube, this one second as a u sub, that one third as an integration by parts, and then secant to the 5th. But if we do add all of those terms together, we get our final answer. Here's the outcome of the first integral. Here's the outcome of the second integral. Here's the outcome of the third integral. And simplifying everything, we get 5 root 2 over 6 plus 4/3 plus 3/2 log 1 plus root 2. That was crazy. That was absolutely crazy for the very, just starting out with this scalar line integral of what felt like a fairly simple curve in a fairly simple scalar field, x squared plus y. But hey, that's what calculus is all about, a little bit of problem solving. I hope it was a good one. We're going to talk about vector line integrals in the next one. You'll see the first application of the generalized Stokes theorem. Looking forward to it. See you then.